So, for those of you who don't know me, I am the product manager for cybersecurity at Hortonworks, which means that I now don't only herd the Hadoop elephants, I also herd the developers who are behind the project as well. In my previous life, you could probably call me a data scientist, just about, in one of the many definitions that's floating around today. And if you want to get hold of me, then I'm fairly active on Twitter. That's my Twitter handle. Feel free to reach out with any questions you have around that. Or, of course, find me on LinkedIn. The advantage of having a globally unique name is that I'm already pre-identified and quite easy to find. So please do reach out with questions if you have any. So, just had to share this. This was something I heard the other day from one of our customers sort of wandering around the conference, which I thought was a great little insight into where we are today from a security perspective, and a very mature perspective on security, which was not really the problem of, well, you know, we've got all our AV logs, and we've got our firewall logs, and we've got all of these event type things. Their focus was on the people. Their focus was on the individual entities that sit behind the keyboards. And her comment I thought was quite insightful, which was along the lines of, I got 10,000 users and 10,000 vulnerabilities. So what we're trying to do with Metron is focus very much on that kind of user-centric approach to behavior and help you measure how well behaved your users are. So what we're going to do now is look at some of the techniques and capabilities that we have to enable that. So as with everything, all data science tend to start with the data. And you can't really have data science without data. So some of the key data sources that we will use and bring into these kind of use cases, and these behavioral use cases include things like firewall logs. So that's everything from the traditional old firewalls to the super smart ones that say they do all the machine learning for you, but really, really can't because they don't have access to the whole data. Things like DNS servers. DNS is a great source for doing things like botnet detection or finding users who are going to weird sites, for example. Similarly, things like server logs, proxy logs do a kind of very similar thing. The other thing is, of course, traditional systems often ignore your custom application logs as well. So we really want to be able to bring pretty much everything you've got in. So your security department now gets to just suck whatever data it wants into it. Then, of course, there's the more traditional ones, things like antivirus logs, things like AV logs, AD logs, AN other logs, all these kind of logs, and whatever you want. We bring that into a very flexible schema, which we then process through an analytical pipeline, which includes the profiling capability I'm about to show you. The other key sources we like, and again, these are things which really benefit from very large scale, are things like raw network taps. So if you can get access to the raw network traffic, then you can get access to pretty much everything. What we tend to do in Metron is we will provide those kind of full-scale captures of everything on your network. But when you're actually looking at that from an analytic perspective, you're usually not looking to process your whole 100 gigabit a second transit link, for example. You don't necessarily need to process every single packet into a profile. So what we tend to do is go take a progressive approach with these kind of data sources, parse them out, use things like deep packet inspection tools like Bro, for example, an open source deep packet inspection tool, and start to look at these things from a more logical level, from a more entity level, from a more protocol type level. Some of the things, to give you a few examples of some of the things we've done recently, we've, for example, pull out all the HTTP traffic from network trace and profile on the basis of that. DNS traffic often comes from that. One of the fun things and use cases that we've found recently around this is pulling off things like SQL traffic from the raw packets. We found that in some environments, people, security want to be able to log and see what people are running against their old legacy SQL systems, but they also cannot even begin to touch the server that it's running on because it's running something so unbelievably important in manufacturing that they can't even get into that server to turn on the logging. So what we do is we just sniff it off the network around the edge. Oh, I can see now. Thank you. The other really common data source that we tend to take from the network taps is, of course, NetFlow as well. So I'd urge anyone who's looking at trying to do decent scale behavior analytics to focus on some of your NetFlow sources. Yeah, for those who don't know NetFlow well, what it is essentially a record of every conversation on your network. So everything that talks to everything else, and for each session. Switches will generate it. Old switches will generate it and get very warm. New switches will generate it without even thinking about it. Yeah, we can also generate it from things like raw traffic feeds in software. It becomes extremely useful for doing things like measuring the behavior of Save App Workstation, which has suddenly decided to turn into a server. And thank you. Oh. That just makes it worse. Absolute star, thank you. Yeah. Thank you. Oh, sorry. So those are the key network sources we're looking at. But what we then need to do is start to put those network sources in context. So the way we do this is we have this constant stream of all these data sources coming in. We will then enrich this with a variety of sources. So the most obvious one is things like user data, asset database data, configuration management data, vulnerability scan data, all these kind of relatively static sources. These all provide context to the kind of profiling that I'm going to talk about. We then also bring in data from the rest of the world. And I'm kind of cheating a little bit here. I'm talking about geospatial data from the rest of the world, geo IP locations, for example. That's kind of moderately interesting. But also things like shared threat intelligence, which can be part of the weighting and balancing of the profiles that you then create against your own data. But the most important context, which is why I failed to animate it properly, is time. So how does the behavior change over time? And that's what the kind of streaming profile event we're talking about today is all about. So what the profiler in Metron does is essentially sort of see all these different data sources that we've brought together. Once we've brought them together, normalized them, added all that kind of static context to them, they then run through the profiler. So what we have here is a representation of these many, many sources that might go through the profiler. The important things to note about these are that they are very, very different in shape, size, and velocity. Yeah, you might have something like this green source is very, very busy. That might be something like a NetFlow feed, which is giving you a very high volume of information. The orange source might be something very specific, like a proxy log feed that's showing you all your requests. And then you've got these kind of weird mixed random sources like, represented by this blue line, which might have things like, I don't know, authentication, log on, log off events, account creation events, those kind of things. So we have these very mixed kind of sources, and all of those then go together into the profiler. What the profiler then does, while it's creating profiles, is to split up the stream into a series of windows and then perform a bunch of analytics on those windows, right? So far, so much like any old streaming analytics platform, right? So what do we actually do that's a little bit different? Or rather, first off, how do we kind of get started with this? So, as I said, this is a technical deep dive session. You are going to see code. This is a chunk of Metron configuration code. I'm showing you stuff that normally would be relatively under the hood from an analyst's perspective. But we're all developers, right? Yeah, good. So this is going to be incredibly simple. This is essentially my hello world of profiles. And the structure is extremely simple. What we're doing is we're just giving this profile unit a name. We can then determine which entity this profile comes from. And what this is going to do is for every message that comes through it, it's going to pick out that field from that message, and that then becomes the key for this profile as to what it's measured. So for every user or every unique user value that comes through my stream, I'm going to get a version of this profile. I then, for each profile window, I start out with my initialization 0. This is a very simple one, and for those of you who remember back to the old days of MapReduce, you'll recognize this pattern as being very, very simple. It's essentially a simple iterator pattern. We will then, for every message that the profile receives, run through this block, which in this instance isn't hugely exciting, and then at the end just dump it out. So it's a very simple process, which then we add on various algorithms and building blocks to make more exciting. So that's how we start. So on top of that very simple iterator loop, we can then add libraries of algorithms to produce data sketches. Data sketches is it's kind of a broad term, and it's kind of a broadly used and occasionally misused term, but essentially the key characteristics of the way that we define data sketches are that they are approximate algorithms which provide fixed size compute and predictable space usage. Some of the ones that we've implemented include things like hyperloglog plus. What hyperloglog plus is it's a cardinality approximation. So we use that to answer questions like, how many unique IP addresses has this server talked to in the last 5 minutes? How many unique servers has a user attempted to log onto? We also provide implementations of Bloom filters, which are very useful for determining things like set membership. We tend to use those for things like rare domains. Have we ever seen this thing before? Yeah, has this user ever seen this thing before? And on top of that, a lot of these things tend to then come together into what we call combined profiles, because we're actually interested in not necessarily an individual statistic, but the behavior of that statistic over time, or the behavior of it against the normal group of users. And that's where things like the T-digest algorithms come in very well. For those of you who actually dug into the Metron code, you probably won't see the term T-digest much. We just call it stats, because the stats functions are all based on that T-digest's mechanism, which provides essentially a very efficient storage approximation of distributions of a variable. Okay, everyone's got a PhD in stats, right? Just checking. I'll dial it up from there, then. The most important thing about these, however, is the fact that they're all fixed size. So they're known, they are known, quantifiable, scalable sizes, which means that we can parallelize them, add up, and know what we're going to end up using, no matter how much data we're going to get, and still not fall over too badly. So sketches are not anything particularly new. They're used in a variety of ways. All sorts of different projects use a lot of the same techniques that we're using in slightly different ways. For example, for those of you who know the Spark project well, you may have come across some of the more recent counter-prox methods. Those build essentially T-digest versions or approximations of counts of things. I think they also added some basic hyperloglog stuff in there recently as well. A lot of the NoSQL databases, for example, HBase, use Bloom filters extensively. A Bloom filter is a structure where you ask it very quickly, is this thing in your set of known things? A Bloom filter will answer, yeah, probably, or no, absolutely not. So it's something which errs on the side of false positives, but it's something which therefore becomes very, very useful for doing things like pruning partitions. We use it in Hive, actually, for partition pruning as well in Hive stats. HBase also uses it to determine, essentially, whether it's worth asking a region if the data is present. Similarly, newer projects like Druid make extensive use of these same data structures as well to do things like approximations of distributions, roll-ups of distributions, and things like that. So what we're using is some quite nicely tried and tested techniques which have been remixed into a different way. And again, I kind of harped on about this a little bit, but the most important element of these algorithms and the determining factor for how we build these algorithms is that we want them to be very, very predictable in the way that they scale. You remember how I mentioned that we send all the data that goes through Metron into a profile. Now that data could be very, very variable over the course of a number of days or over a day. If you get hit by a DDoS attack, you're going to get a lot more data. If you've got people who have normal working hours who are not like me, then you might have peaks during the day. And they might even get some of the evenings off. So you're going to get very different shapes and size of data over the course of these profiles. But with those data sketches, what we're doing is for each window in each sketch we record, whether it's got 1 million events in or whether it's got 10 events in, the size of that data sketch is going to be exactly the same in terms of space consumption and in terms of compute consumption. That makes it very easy for us to predictably scale how much memory, CPU, disk, etc., you need to store these profiles. They're also quite small, which means you can store them for a long period of time. One of the big problems in security is essentially things like, I can't store my log data for long enough because I just can't get enough disk. Even if you can't store the full log data, which you absolutely can in HDFS because it's way cheaper to do so, then you can store profiles for a lot longer as well because they're a reduced, compressed approximation of the data. So if you look at something like one of those cardinality profiles of how many things has a user logged onto, those are about 2.5K each. Now, if you're taking something like a 5-minute window, then that adds up to about a year's worth of data being 250 megabytes. When was the last time anyone heard anyone from Hortonworks talk about something in terms of megabytes? These are so small that we can shift them around quite fast. So that also means that a lot of it, that's a whole year's worth of fine detail of a profile. That also means we can shift them about quite fast and keep them in memory and recombine them and do quite nice computation on the real-time stream. So for every event that comes in, we can essentially query that event against a year's worth of data. So imagine taking, say, your raw authentication logs, which over the course of a year might be, I don't know, what do you reckon? There are a few people in here I know have got some fairly sizable logs, but let's call it 100 terabytes of logs over the course of a year. How many streaming systems do you know that can run a real-time query against 100 terabytes of data? No, we can't either, of course, which is why we created the profiles and why we create that approximation to be able to do that. But what we can do with these is get, within a reasonable confidence interval, the effect of that query over that whole year's worth of data while we're running the real-time stream. So let's just break down how these sketches work with these profile sources. So as I say, the profile's breaking things down in Windows. We saw that little iterator. I'm producing this bunch of sketches, which is great. Okay, right now I've got a bunch of little grouped windows of analytic. The other feature of these data sketches is that they're combinable. So things like that hyperlog log, you have a cardinality estimation, right? Or well, let's make the math simpler. If you want to do something like an average, everyone knows that you can't just kind of take a bunch of averages, sum them up, and take the average, right? Especially not if you've got different numbers of events within your windows. T-digests allow us to combine those data together in a meaningful way and record both sides of that so that we can actually grab an average or a percentile within, as if the window were very different. So we can slice and dice these windows and recombine them so that even if we've recorded on, say, every 5 minutes, I can look at every 15 minutes, or I can look at every day as if I'd recorded that individually. Does that make any sense? So I can take a window which is going from, in this case, the beginning of time, all the way up to my third sketch, because I got bored of drawing boxes after a while. That could be any arbitrary number of sketches, and combine all those together. The other thing I can do, though, is pick and mix these things. So I can skip sketches, or I can exclude sketches based on time periods. So for my second combined sketch here, I'm just picking the blue one and the green one. I don't care about the stuff in between, or I've excluded the stuff in between explicitly because maybe that was a weird day, or maybe it was a holiday, or maybe it was a weekend. So that kind of brings us on to what I think is the most fun part, which is this kind of weird windows that we have. We start off with the most boring window. It's a very simple one. We would configure a window based on, say, the last 30 minutes. I might have been building profiles every minute, but I'm just going to grab back the last 30 minutes from now. Right, simple enough. Any streaming system can do this, pretty much, if you've got enough RAM to hold that stuff. The more interesting stuff comes when we start to use this profile window function, which actually has, it all sounds quite a nice kind of relatively English-feeling DSL to it to configure this. I apologize to our European colleagues, but it is English-based. That said, there is some interesting localization we'll come on to. So the way this breaks down is, you see this 30-minute window every hour, starting yada, 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 yada. So what we do is we essentially specify the length of the windows that we care about, so the length of units of time we want. So this might be, I'm interested in 30-minute chunks as a baseline for what happened in the last minute. I'm going to pull them back for every single hour of a day. This might actually be for the current hour of a day. So if I'm doing, say, user comparison, I'm comparing a user's behavior right now, then I might pull back the last hour worth of their behavior for every, or for the same hour of day. Yeah, because they behave differently when at noon than they do at midnight. We then specify the overall time range of this, which is bringing, essentially the capture period for this. And here we've got quite a lot of flexibility here. I mean, I've written it out in full here. It's starting from 2 hours ago. That could also be starting from, or in fact, actually, you don't have to keep saying starting. You can just say from if you're feeling terse. But yeah, and that can be units of often days. Days are very common in that. There are people who go back for years. Although actually, we don't support years. I think that was probably the developer being nervous about scale. But if you scale, then you can do it in 365 days. But they were a bit lazy about saying actually you can put word years in there. And then of course you've got a finishing period as well, which is expressed in a very similar way. So let's kind of riff on that function a little bit and see what else we can do with it. So here we've got a slightly different breakdown. You see I've skipped the starting because I got bored of typing. And I've got this very similar window. But I'm also saying excluding weekends. So I can add exclusion lists, inclusion lists. And those can be lists, those can be terms like weekend, or they can be terms like weekday, or they just Mondays, or whatever else you want out of that. I can also build in holiday libraries as well. So there's some quite nice libraries which index and record the holidays. So this becomes very, very useful for people who don't just work through their public holidays. If you've got this kind of library, then I can say, right, okay, these users are in New York City, so I'm going to exclude the baseline for their normal behavior. I'm going to exclude things like Memorial Day and all the US holidays. So that kind of, I actually be excluding. I'm being very exclusive with this. You can also use include, should you actually really want to be interested in holidays. So if you're building, say, a profile that's there to detect people who are coming into the office at strange hours and doing things that they shouldn't, then obviously the including function becomes much more useful for that. So let's put some of this into action. Let's go catch a hacker. That animation didn't quite work, but here's a lovely visualization from one of our partners. Can anyone spot where the hacker is on the visualization? I was meant to give you the clue in a few seconds, but I'm pretty sure everyone got it anyway. So on a visualization like this makes it very, very easy to do this kind of link analytics. This is on some authentication data, and very easy to see the people that absolutely pop to the top for doing bad stuff. What we're looking at here is an individual user in the middle who's then logging on to a large number of servers. The data comes from a red team exercise that Los Alamos Labs did. They would very kindly anonymize this, put it all on the web, and said, security researchers, go nuts. So we did. So what we then wanted to do is sort of say, right, okay, it's very easy and very powerful to have an analyst look at a graph visualization like that and go, huh, a pattern. However, what that can't do is deep long-term automation. What we need to be able to do is take the capability of a human being to look at that and go, yeah, that's the bad guy, do something, and turn that into something which is a capability of a stream to be able to recognize those patterns of behavior automatically. Because what I might well want to be able to do is say, right, yeah, that one's so utterly obvious and it's so utterly computable that I don't even want a human being involved in that one. I just want to shut them down right now automatically from an orchestration tool, which gives me a much more instant response to these kind of detections. So how do we do this? You know what? Actually, first I'm going to show you our approach to how we've done that. And I've been logged out. Nope. You know what? One of my other favorite examples of this is the fact that you can personalize things like login failure counts to people who can't type the word password. Right, so let me just, my cursor's disappeared. There, okay, yeah. Let me just bring this set up. Right, okay. So this is that same data set. It's actually the exact same data set that we put the visualization on, but this is once it's gone through Metron's detection. And I'll make that a little bit, I'm going to zoom into relevant bits for you. And yeah, what you'll see here is we've got a bunch of these very highly scored alerts, which are generated by the profile. Now, if I dig into one of those, I'm going to dig into that one, then I get a lot of details on this alert. And you see a few extra fields here. What we've got is you have a number of distinct auth attempts over the period. So it's actually an average over a period because not many people have managed to log on half a time yet. It's kind of binary, right? But we've also then got some comparisons from a broader group. So we've got that median comparison that's been drawn out from the profile. We'll show you how this build in a moment. And the deviation within that group as well. So we've got there a baseline group and an individual user over a period. What we then do is combine those together into a rule which says, sorry, I can't quite get the zoom. We combine those into a rule which says, okay, this user attempted to log into too many machines in this period. And instead of being a traditional SIM type rule, I'm automatically baselining that against a profile of the group that that user belongs to, instead of saying like, well, more than 3 is probably bad. That personalization comes from that scalability that I was talking about earlier. Because we can predictably scale the number of these things and the size of these things that we're going to need, we can do that kind of deep personalization predictably against a user's network. So let's see what actually went into that. And we got our familiar profile structure, very, very simple. It's like for every user we see, we're going to create one of these windows. But in this instance, we're using the hyperlog plus implementation there. So we just start it up. Then for every message, we're going to log the host that they log into, that they attempt to log into. I can also add things like filters if I want to get rid of certain types of data, or if I don't care about other things, or I don't want to count failures, for example, as an attempt. I then push that out into a profile, into a result called profile. So fairly straightforward. What I can then do, though, is also kind of profile the profiles. So out of my hyperlog profile, what I'm going to get is I'm going to get the cardinality of that login. So for each window, I'm going to get the number of servers that that user logged into in that window. But yeah, that's not hugely interesting for building baselines. So what I do is I add this triage output, and what that does is send the result of my profile out to back around the loop of Metron processing, so that I can then put it back into the profiler again. So I can profile my profiles to create baselines of that behavior across different groups. That's what I'm doing here. So you'll see, I mean, here, I'm building a profile based off that source type of profiler. So that's that same loop which has come back around again and is being reprofiled. Here I'm creating one of those tdigest stats loops. So I'm just creating the distribution. Now, one of the interesting things here is that my for each is different. It's no longer by user. Could be by user. Maybe you do want to look at just the baseline against an individual user's behavior. But yeah, in the real world, what we found is that's much more likely to be something like an AD group or a kind of functional group or a departmental group, because that tends to be a better selector of people who are going to behave a little bit alike. So again, just building up very simple profile. We now got our 2 profiles. So we've got a profile of how many things people log onto. We got our profile of that profile. Make sense? Right. A little bit further down the rabbit hole. What we then do is we grab those together into writing a rule. And you can see we we were replaying the data extra fast, so our windows aren't particularly interesting on this one, because from 6 minutes ago is like, well, yeah. But that's just an artifact of the fact that we didn't want to wait around a month for the demo to run. So we're grabbing back our profile windows. We're then using that, the individual user's profile, and you can see we've showed off a little bit there about the way that we've combined those statistically to get means across those profiles. So I'm getting back all those windows, and then I'm able to recombine them and recalculate them on the fly. We're then getting back our baseline distribution profile against the global lot, which is essentially how we build up our baseline. And then we've got actually this one's an additional one, which is based off that first hello world count example we saw. We often use these kind of things to say, right, okay, now I've got some specific targeted profiles which are about a specific behavior. In this case, logging into number of servers they've logged into. But what I'm actually interested is not, I can care less how many events the user has done. I want to actually know how risky is that user being right now. Yeah, how much should I be sending HR after them to shut down their machine right now? So what I then do is I create those kind of profiles of an individual user and their overall behavior at a kind of higher level. So you get that sort of roll-up of effects which contribute towards the risk of an actual entity moving away from just the individual log events that you've seen. Hope that sort of makes sense. So that's one of the sets of profiles. I want to show you another example here of, if my cursor comes back, can anyone see where the mouse went? Yeah. I think it's been putting cheese on my laptop. The mouse has run away. This Geohash use case. Oh, wow, look, people, yeah, we caught some people. So this, again, is based on a slightly different set of profiles and some capabilities that we've added reasonably recently to the profiling. And what you'll see here is this is a user who has logged on from somewhere weird. What we're doing here is creating geohashes. Is anyone using geohashes elsewhere for anything? Yeah, they're becoming much more popular because they're awesome. So what a geohash is essentially it's a hash code which takes latitude and longitude pairs and breaks them down into essentially a series of hexagons that cover the world. And the size of your hexagon is essentially the length of your geohash. So to give you an idea of what that kind of means, I looked up the latitude, longitude of roughly where we're sitting right now, converted that into a geohash earlier. So that top geohash, which is, that's like a 10-character geohash, isn't it? Can I count? Is that 10 or 11? I can't count. It's 12. Oh, so it's full-length geohash, yeah. So that geohash, of course it is. That geohash will give me my location within about 20 meters. But as I start to chop characters off that, I get lower and lower granularity. So I get from, like, you're in this room to you're in this city to you're in this country to maybe you're in this hemisphere if you start doing some one-character hashes. This is great because it really helps you debounce very noisy geospatial data. Lots of people use it for things like GPS tracks to kind of normalize them and join them to regions, which is a kind of, yeah. If anyone's really interested in that, by the way, I have a sideline hobby in Markov models for map matching, which is, yeah, I'm always happy to talk to anyone who understands. But yeah, so yeah, lots of people use it for things like GPS. We use it for things like geo-IP location because we find that if you try and do pure latitude, longitude joins, then you kind of wander around a little bit and you never get a proper join. So they make it very efficient to process in the stream as well. So what we're doing with these geohashes is we're computing the geohash of the geo-IP location where someone's logging on to a VPN, for example, or logging on to a system. We then store those as a set of profiles by the user. And in this instance, you can see that for this individual user, this login event has sort of wandered out of the distribution of what is normal for where they normally are. So I can record centroids of where a user normally is. So maybe they normally log on from work, they normally log on from home. I've then got two fairly standard points. As soon as they start logging on from other places, which are unexpected, then we can start to flag that anomaly. So that, again, is a combination of the profiling of an individual user's behavior based on a specific event, which then contributes towards that user's overall risk score, which combines back into a nice view of who the bad people are. To show you how that comes together, again, very simple. This is another one of the algorithms that we've recently added, which is this multi-set data structure, which then allows us to store an individual user's multiple locations over time and start to create essentially the kind of slightly wandering central space around which that user is usually located. What we then do is in our rules, again, that's that mergeability is absolutely key. What you're seeing here is a kind of compressed version of the code you saw before, which is this profile get, just the locations of that user within the window, smush all those together and pretend that they were just one set. So combine all the multiple instances of that set into a single set, which gives you a nice kind of exclusivity of that. We've then got various, we've also added a number of Geohash type functions into that as well. So rare domains, we use Bloom filters for that, but I want to get on to another exciting new thing that we've added, which is typo squat. Typo squat is kind of an interesting case. This is taking some of the stuff that we've done with a streaming profile, actually extracting it back out into a batch type piece. So we still do the streaming query on it, but we kind of pre-prepare profiles in batch for typo squat. Does everyone know what typo squat is? How many people have logged onto Facebook or Goggle or Gog1L? That's typo squatting. It's when a malware tries to make a domain, or when spearfishers, for example, try and make your domain look a lot like your domain. And you might do that with things like just shifting the bits around a little bit, or shifting characters, or you might do it by characters that look a lot alike. So you have a 1 for L thing will fool most people on a nice big screen looking at their email fast. So the way you do this is you build up all those permutations of what could likely be typo squatted, and you turn a list of 10,000 domain names into a list of a little over 3 million potential typo squatted versions of those domain names. So this is something which very rapidly becomes a big data problem and a big set problem to challenge. So what we then do is we put those all into Bloom filter so that we can query them fast in real time. And the way we do that is with a structure very similar to your same kind of principles, same kind of functions as you use with the profiles. In this instance, you see I'm building a Bloom filter that can hold my 3.5 million entries. I'm then putting my typo squat versions into that Bloom filter and just merging it all together and then hosting that out onto HDFS. So if I'm going to show you the, I've been kicked out again. This is terrible. So I'm just going to show you quickly on the command line this. So this is very new, so we haven't quite got the GUI up on this yet, but for those of you who are common Metron users, by the way, this is how you don't have to keep typing the zookeeper URL. So what we're going to do is we're going to interact with that language. We've got a REPL-based approach to interacting with that language. We do also have a web UI which allows you to configure this. But what I'm going to do is just have a look at some of the things that result, or some of the typo squats that we like. So does anyone have a favorite domain? Hortonworks.com, okay. Someone had to say it. Right, so how many combinations do we get from Hortonworks.com? Okay. These are all the proposed typo squat replacements for Hortonworks.com. You get quite a lot of these things. They add up really fast. So what we do is we push that into that Bloom filter, which you can then store in memory and query in memory fast at real time. Some of you who've probably got experience with HBase are probably asking us things like, why aren't we just doing this with an enrichment using HBase's Bloom filters? The reason is that's slower than we want. We don't care about getting the actual result. We just care about whether a result exists or not in that set. So we've kind of essentially taken the best bits of some of the indexing capabilities out of other database engines and kind of gone, we don't care about the actual data, we just need the index or whether the index functions or not. So that then gives us some capabilities to do some very, very fast real-time querying against this database, which is why, for example, if I see, my mouse has gone again, right? Okay. If I look at this, for example, this is, let me just hook up to the proxy, and I am going to go to, let's see, google1.com. This is probably not a real typo squat domain, but if I browse to that, oh wow, someone has actually bought that one in the hope of probably launching an attack on it. So I've just done that through a proxy that's hooked up to this Metron. That data is then going to come through shortly, if my VPN will let it. And you see it's found that, oh dear, how embarrassing, I haven't actually loaded the full size of that. But yeah, it's found that instance, and yeah, here's one I did earlier, where it's actually found an instance of typo squatting against that domain from the request that I made. I think that was yesterday. And it has identified this successfully from that Bloom filter as part of a real-time stream. And that happens in actually a matter of milliseconds, so you can kind of scale it to quite large varieties. So, with that, thank you very much. I hope that's shown you some of the interesting new things. And if there are any questions, I think we might have a few minutes, but I'm very happy to take questions. And if you want to get in touch with me or learn more about the Metron project, then that is our website. That has links to things like the GitHub. Please feel free to join the community, join the dev lists, join the user lists. They're very friendly places. And if you have any questions for me, then feel free to reach out anytime. And thank you very much. And if anyone does have any questions, I'm probably just going to hang around and disrupt the next session.